All right, this is Advanced Placement Chemistry, day 41. This is the ideal gas law. And this is an assignment that's due on Friday. You do have a test on Thursday. It should be in absolutely by next Monday at the latest. So let's go ahead and work these problems. So you have a 12-liter glass container. Now what that means is when you see those words or words like that, it means it's fixed volume. So that means the volume cannot change. It can't get bigger, it can't get smaller. So that number is never going to change in the problem. It holds oxygen gas at 1.21 atmospheres and 289 Kelvin. Now, any problem you work in gas laws has to be in Kelvin, so that's already done there. The temperature is increased to 308 Kelvin. What's the new pressure? So this is just simply what's called a plug and chug. You just put in the numbers and you solve the problem. Okay. So what we're going to do is the P1, the initial pressure. The ones are the initial conditions, the initial state. The 2 is what you have after you've changed something. It could be one variable, it could be more than one variable, but in most of these problems, at least initially, it's just going to be a single variable. Let's go ahead and plug in the numbers. So we have a P1 of 1.21 atmospheres and a V1 of 12 liters, that's the volume. And that's all going to be over the initial temperature, which is 289. And that's going to equal P2. Well, that's what we're trying to find out, the new pressure. So we're just going to call that P2. And then the V2, the volume afterward, we said that this volume cannot change. So it's going to still be 12 liters. And that's going to be over the new temperature, which is 308 K. So at this point, it's just a simple algebra problem. Since the volume hasn't changed, those cancel out. And now what you simply do is multiply both sides by 308. It's just an algebra problem at this point. And this side over here, I'm going to multiply by 308K. Okay, so these two cancel out. So it's 1.21 times 308 divided by 289. And what we get is that the new pressure, P2, equals 1.29 atmospheres. That's your answer. Okay, let's move on to the next one. Okay, so this one says a balloon with an initial volume undergoes an increase in temperature from 341 to 579. So we have a volume, we have two temperatures, and a pressure increase, and we're given two pressures, a beginning pressure and a final pressure. What's the new volume? What I always want you to do in any chemistry problem is write the appropriate formula. So eventually you memorize them. You're not required to, but the less you have to think about on an advanced placement test, the more formulas you have just at your fingertips, the less you have to think on a test, and that's what you want. So it's going to be P1, V1 over T1 equals P2, V2 over T2. All right, so let's plug in some numbers. So the initial pressure is 1.23 atmospheres. The initial volume, V1, is right up here, 2043 liters. And the initial temperature is 341 K. Again, since temperature is already in Kelvin, not in centigrade, we don't have to do anything. We just plug it right in. Okay, and afterwards we have P2, which is 3.47 atmospheres. Times V2, well, that's what we're trying to find. We're trying to find the new volume, so we're going to call that V2. And that's over T2, which is 579. Okay, and what we get is V2 equals 1, 2, we're just going to call it 30. And that's in liters. So let me get on screen. There you go. So that's your final answer. Okay, and for number 3, a glass container, so you know it has a fixed volume. The volume can't change on that. Holds CO2 gas at a temperature of 85 degrees centigrade and 104 atmospheres. The temperature is increased to 142 degrees centigrade. What's the new pressure? Well, first thing is the moment we see centigrade, we need to convert to Kelvin. So Kelvin equals 273. And you should put the 273 first, even though this is an addition problem. The reason is, if this was a negative temperature, you could be subtracting it. So it's 273 plus 85. And that's going to give you 358 Kelvin. And then down for the after temperature, it's 142. So it's going to be 273 plus 142. And that's going to give you 415 K. So now we have temperature in units that we can work with in a gas equation. All right, so let's set this up. So a gas container holds CO2. So let's go in. So P1. So our initial pressure is 104 atmospheres at the beginning. First of all, I'd like you to write the equation. It may seem tedious, but it pays off when you have a lot of equations memorized and don't have to be searching around or hoping that there's one on the formula sheet that they give you. Okay, so P1, pressure 1 is 104 atmospheres, 1.04 atmospheres. Okay, V1, it says a glass container. It doesn't give us a volume. So we're just going to call it V. Since it doesn't change, we don't have to call it V1 or V2. So this is kind of a key concept. Since it's a fixed volume, it's just going to be the volume V. That's all we need to know about it. And that's divided by the temperature. The first one we have is 358. And then that's going to equal P2, well, that's what we're trying to find, so P2. And the volume doesn't change, so there's V again, the same volume it was on the other side. And then you divide that by the new temperature, which is 415. Okay. All right, so volume is going to cancel right off the bat. You got a volume on both sides on the top, it just cancels out. So now we simply have P2 over 415 equals 104. Over 358, so that simply becomes a simple algebra problem. And that gives you 1.21, if you want to call it, that's 1.21. So pressure afterwards equals 1.21, and the units is atmospheres. You don't have to do any conversions between units. If it gives you to you in atmospheres, use atmospheres. If it gives you to in kilopascals, use kilopascals. You don't need to make any changes. But we'll see later on when you do have to make conversions between different units of pressure. Okay, here we go. Now we're going into the really important law, the ideal gas law. And this is a really important one because it has moles in it. So it allows us to convert things into moles, which we can then use in a chemical equation and do some real chemistry. All right, so solve the ideal gas law for pressure and show that the units all cancel to produce units of ATM. So this is called the gas constant. And it's this number, and it's all these different units wrapped together. It's basically a lot of different conversions wrapped together. And it's designed so that whichever variable you're solving for, all the units will cancel out except the units of that particular variable. And that's what the point of my asking you to do this problem is. So let's go ahead and let's write this out. But you put the units of measure behind each of the variables. There's no numbers involved here. So let's go ahead and do that. So pressure in atmospheres times volume, just following the formula, in liters equals N in moles times R, which is in latum over molk, liter atmospheres over moles Kelvin, times T, which is in Kelvin. So in other words, what we're going to do is we're going to divide both sides by V, because we want to know for pressure. So we're going to solve for pressure. So that means we divide both sides by V. And this cancels out. So now we have P all by itself, so it's solved for P. So what we want to see is, does all of this over here give us a unit of atmospheres? So let's just see. While we have moles here and here, they cancel. Should be an L there. Moles here and here, they cancel. We have Kelvin here and here, they cancel. Okay. You have liters in the numerator of a numerator fraction. So up here, this fraction is in the numerator of the bigger fraction. So the liters is in the numerator of a numerator fraction. The liters down here is in the numerator of a denominator fraction. So those will cancel. And if you need practice with that, you'll get used to that. So liters cancel. So the only thing we have left standing is atmospheres, and that's what we want our final answer to be. So the R made everything cancel out over here except the one we wanted to end up with, the last man standing there, and that's atmospheres. So that was the point of that problem. Let's do it one more time for temperature, okay? So we're going to write PV. Whoops. With the units. So pressure in atmospheres. And try to do this on your own before you watch this. But I'm going to go ahead and do it here, of course. And the volume in liters equals N in moles. That's the number of moles. R in latum over molk. And T in Kelvin. All right. Okay, so now we're solving for T. That means we got to get rid of N and R on this side of the equation. So we're going to divide both sides by N and R. I'm just going to save myself a little time and put NR down there, and they cancel and cancel. Now I have to write them over on this side. So I have N in moles and R in latum over molk. All right, so let's see what cancels. So you have atmospheres in that, since there's only one level up here on the numerator, this is the numerator level of the numerator of the big fraction. So you have in the numerator part of the numerator fraction, you have atmospheres, and in the numerator part of the denominator fraction, you have atmospheres, so those cancel. You have liters in the numerator of the numerator fraction and liters in the numerator of the denominator fraction. This down on the bottom is the denominator fraction. So that's L and L cancel. Okay, and finally you have down here on the bottom only, you have moles in the numerator of the denominator fraction and moles in the denominator of the denominator fraction. So they cancel. So the only thing you have is K in the denominator of the denominator fraction. But remember, when you have the bottom of a fraction on the bottom of a fraction, remember how you do fractions, you flip. When you do the flip and multiply, the K goes up on the top. So I can rewrite the K up here. And so my final units, my temperature in K ends up here, and it's over here. So we end up with the same units. So R successfully cancels all the other units except the ones that you're looking for by the end of the final equation, okay? Okay, number 6. A gas is held in a 0.36 liter container, so that's volume. Let's get used to these units. At 89 degrees centigrade, that's temperature in centigrade, and 0.97 atmosphere, so that's pressure. The question is asked how many moles N of the gas are in the container. So the fact that you see N in this problem means it's a ideal gas law and not a combined gas law or Charles or Boyle's or Gay-Lussac's. It's got to be an ideal gas law. So first thing we're going to do is the moment you see centigrade, you're going to convert to Kelvin. So it's 273 plus 89. And that's going to give us 362 Kelvin. So now we have the temperature we can work with. Okay. Finally, secondarily, it's asking for moles. So we're going to do our algebra first. I always believe in doing algebra first, not plugging in numbers and then doing algebra. So it's PV and RT. So we're going to divide, write this, we're going to divide both sides by RT. That's going to, and both sides, this side as well. And that's going to give us N equals PV over RT. All right, so to get that, so we plug in our numbers and we get N equals, pressure is 0.97 atmospheres. Volume is 0.36 liters. Over R, which is 0.082. I know I went to 06, but the book, your textbook goes to just a 1, so that's good enough to cut it off there. And you're not always going to have to write out these liters. When you become satisfied that you understand, Latam over Molk. Okay, and finally on the bottom we have temperature in over here, 362. No, let's try that again. Okay. So again, just since we're new at this, let's practice our units. So we have K on the numerator of a denominator fraction, and then the denominator of a denominator fraction cancels. We have liters up here and liters down here. They're both in the numerator of their respective fractions. We have atmospheres up here and atmospheres here. And we end up with moles in the denominator of the bottom fraction of the denominator fraction. So that means it flips over and goes up to the top. And that's what we want because we want our answer to be in moles. So now you can just crunch the numbers here. Don't forget that 0.0821, not just 0.821, or you end up with a lot of wrong answers. And that gives us 0.02. So 0.012, excuse me. And that's moles, is what we were looking for. So now we have a number of moles that we can now stick into a chemical equation and do our chemistry. All right, so that's why this equation is really, really important in chemistry. All right, let's keep going. Let's do 7. It's asking really for the same thing, all right? So we're going to write PV. Always write the initial equation. We're looking for moles. And we end up with N equals PV over RT. Okay, next up, I got to convert centigrade to Kelvin. And that's going to be 385. Right there. All right, and I think we have everything we need. No, we don't. What else? What's different about this one? This is in kilopascals. Now with combined gas law, Boyle's law, whatever the pressure they give you, you can just go ahead and use that. But in this equation, pressure, because of R, pressure is expressed in atmospheres. Okay, so the pressure has to be in atmospheres. So we have to do one more conversion. So that conversion is going to be, we have 112 kilopascals, and now we need a conversion. And if you go back to yesterday's assignment, there's 101 kilopascals for every 1 atmosphere. So let me write that down. I'll write that way over here because I have some space here. 1 atmosphere equals 101 kilopascals. And you'll get to know these very, very quickly. So it's going to be 1 atmosphere. That's what we need to have over 101 kPa. And that's going to give us 1.11. So that's 1.11 atmospheres, ATM. Now we have all the numbers that we need to plug into the equation. So let's go back and do that. I'll do it down here. N equals pressure, and that's right here, 1.11 atmospheres, times volume, right there, 3.2, over R. And I hope you're satisfied by now that R works. It'll cancel the units properly to give us moles. So I'm not going to write the units down here. It's 0.0821. And temperature. Temperature is 385 Kelvin. Okay, so now you just do the math on that. And we get 0.11. So I'm going to go ahead and I'm just going to write that up here. N equals 0.11 mole. And again, you have a number that you can put into a chemical equation. We have to have moles to go into chemical equations. All right. 8. If the gas had been CO2, because up here it said it was helium. If it had been CO2, would the number of moles been different? No. Doesn't matter. Doesn't matter what the gas is. No. Just put a big fat no there. Okay. Just put the element or compound does not matter. Because we're really not doing chemical equations here, whether CO2 is chemically different than helium. We're simply doing physical relationships between pressure, temperature, volume, and moles, number of molecules, in other words, or number of particles. All right, let's keep going. Okay, number 9. If a sample of gas is held in a fixed volume container at a constant temperature, so you know a couple things. That the volume equals a constant, that's not going to change. And a constant temperature, so T equals a constant, that's not going to change. What is the relationship between the number of moles of gas and the pressure of the gas? So it's kind of a vague question. I don't expect you to really know what I'm asking here by yourself. Maybe you do. But what I want to do is establish a relationship that's important in the future that we're going to use a lot. So we're going to write PV equals nRT. And we said that volume and temperature are constant, and we know that R is always constant. So what I'm going to do is I want to know the relationship between pressure and moles. So what I'm going to do is divide both sides by V. And that's going to give me, the equation looks like this, P equals N. And now the things that we said were constant, V, R, and T, I'm going to lump together. Cancel that. I'm going to lump together into a set of parentheses. So we have R, T over V. So this clearly kind of illustrates what the relationship is. That that pressure is directly proportional to number of moles. So in other words, if these things are just a constant, they're just some number, it could be 10, then if I double this number, I double this number. If I triple this number, I triple this number. If I cut this number in half, I cut this number in half. So that's what I want you to see. So the pressure of any gas, all the rules we're writing apply to any kind of gas. There's no difference between carbon dioxide and helium. Of any gas is directly proportional to the number of moles. And you can just parenthetically give yourself a quick example. Parentheses, double the moles, doubles the pressure. Okay, just to remind yourself what that means. So you double the number of moles, you double the pressure, okay? And any other relationship you want to do there. Okay, so whatever happens to this in terms of multiplying it happens to pressure correspondingly. All right, let's keep moving. Okay, so this one's from your book, and it's a fairly basic problem. Assume that you have a cylinder with a movable piston. What would happen to the gas pressure inside the cylinder if you do the following? Okay, so here's an animation of a piston and a cylinder. This is the type that you have in a car. It's called a 4-step compression piston. But what you see is, you see this thing that looks like a can of soup going up and down. Inside the area inside the chamber there, where you see all the coloration, is the cylinder. So that's what they're talking about. Now this is one where the gasoline is exploding and causing the piston to move. But what they're talking about in this problem is that the piston is compressing down on the gas. So I just want you to see an illustration. A lot of students I've had don't know what a piston is and a cylinder. All right. Okay. So they want to know what would happen. You have a cylinder with a movable piston. What would happen to the gas pressure inside the cylinder if you do the following? You decrease the volume. So you push that piston down into the cylinder. So you decrease the volume to 1/4 the original volume while holding the temperature constant. So the way we can do this is, let's just set up the ideal gas law. So P, and then kind of space things out here. V equals N R T. And so we've decreased the volume to 1/4. So we're going to multiply volume by 1/4. And we want to know what's going to happen to the pressure. So we said that this is constant. This is always constant. And number of moles, so we're not changing the number of atoms or molecules inside, is constant. So these all equal some number that's going to stay constant. So if we cut this down by 1/4, this is going to have to go up by 4 times, because these two have to offset each other so that this number doesn't change. So let's just make up a number. If this was 40 and we cut this down by 1/4, this would have to go up by 4 to keep this number at 40. And that's what they're saying. So it's good. What the answer is, the pressure will increase by 4 times. All right, next. You're going to reduce the temperature in Kelvin, it's got to be in Kelvin, to half its original value while holding the volume constant. Okay, so let's go ahead and write PV. All right, so number of moles is going to stay constant. We're not changing how much gas we have there inside. R is always constant. And it says holding volume constant, so this is constant. So what they're saying is you're going to cut the temperature in half. So this is going to become 1/2 of this. So if you want this whole equation to remain in balance, you have to cut the pressure in half. Okay, just basic math. Anything you do to one side, you have to do to the other. So the answer would be the pressure is cut in half. By the way, there was a standardized test once. They used to always ask the question, and they used the expression, rather than say cut in half, because that's kind of a colloquialism, they said, use the term halved, H-A-L-V-E-D. That word, just in case you ever come across it, means cut in half. Okay, next, reduce the amount of gas to half while keeping the volume and temperature constant. So one more time, we write out the ideal gas law. Okay, and we say volume is constant, and we say temperature is constant, and R is always constant. So these are the only two that are variable. So you cut the number in half here. So to keep the equation in balance, you got to cut the pressure in half. So it goes to what we said up above, that the pressure is directly proportional to the number of moles. If you have half as many molecules or atoms flying around inside that container, it's only going to have half the pressure. So the pressure will be, watch this, halved. Cut in half, okay? And that's that. Okay, let's go ahead and do number 11. 11 and 12 are kind of challenging. They come from your textbook. So you are given two flasks at the same temperature. So I just kind of like to write T equals C for constant. One with a volume of 2 liters, the other with a volume of 3 liters. The 2-liter flask contains 4.8 grams of gas, and the gas pressure is X. So they're not even going to give you a number, they're just going to give you it's something. The 3-liter flask contains 0.36 grams of gas, and the gas pressure is 0.1X. So you have a relative number relationship of pressure. This one is 10 times this one. You don't know the exact number, but you know a relationship. That can be helpful sometimes. Sometimes that's all you need to know. You don't need to know the exact number. Okay, which of the two gases contains the greater molar mass? So what we're trying to do is find the molar mass of the two gases. So what does as a molar mass? Refresh yourself. It's grams of whatever the substance is over moles. So we're trying to find grams over moles. Well, we can see right here in the problem, they gave us numbers of grams of each of these two substances. So right away, we know what that top number is going to be. What we got to figure out is what's the bottom number, moles. All right, so let's start with, so let's start with the first one. Okay, so here's what I'm going to do. I'm going to write two ideal gas laws, one for each of these situations. And we're going to call the first situation A. So in the first one, I have P, A, the pressure in situation A, times V, A, the volume in situation A, equals N, the number of moles in situation A. That's the first one of these two. And then R is always constant, so I don't have to label that A. And they said T is the same for both. So I'm just going to call it T. I don't have to say for situation A. Now for situation B, same thing. I got P, B, V, B equals number of moles of B, RT. All right, so now what I'm going to do is I'm going to make a ratio of these two. And I'm going to fill in the numbers that I know. So the pressure in A, that's the first one. So you're given two flasks, one with 2 liters, the other with 3. The 2-liter flask has a gas pressure of X. So the pressure of this one in situation A is X. The volume is 2 liters. And that equals some number of moles of situation A, which is what I'm going to try to find because I need to find a denominator for each of these fractions. And then it's RT. So whenever you have a relative number of something, that this is X and this is 0.1X, but they don't give you specific numbers, you can often set up a ratio and get things to cancel out. So for situation B, that's the one where the pressure is 0.1X. And that's the one where the volume is 3 liters. And that equals the number of moles of B, RT. So we've set up a ratio. So what we're going to do now is we're going to cancel the R and the T because they go away. And we're going to simplify this. So we have 2X. I'm going to drop the unit of measure right now. 2 times X pressure equals NA. And 3 times 0.1 is 0.3X. Just multiply this times everything there. And that equals the number of moles of B. So, and that's, we're going to keep that as a ratio. So the ratio of moles of A to moles to B is 2X. So the X's cancel. And it's 2 over 0.3. And if you get that, do the math on that, that gives you 6.7 moles of A for every 1 mole of B. We don't know how many moles we have because it didn't give us an exact number for pressure. But we know that ratio. So this is moles of A and moles of B. All right, so now we want to know the molar mass of each. So I'm going to come over here and I'm going to do situation A. I'm going to move over here so we have a little space. So situation A, so we're moving back over here. The grams of A, what's the grams of A? That was the 2-liter one. So the 2-liter flask has 4.8 grams because we're going for grams over moles. Okay, for every 6.7 moles. We don't know that's the exact number, but it's a ratio. It's almost like an empirical formula. It's the lowest common denominator ratio of these two. For B, we have this. We have 0.36 grams of B over 1 mole of B. And I should put mole of A here. Okay, so do the math on that, and what do you get here? You get 4.8 divided by 0.67 divided by 6.7, and that's going to give you 0.72. Getting a little crowded here. And 0.36 over 1 is obviously going to be 0.36. So all we have is a ratio of the number of the molar mass, but this is the a ratio at least. That's grams per mole of A and grams per mole of B. That is the definition of molar mass. We said that over here. So we find that the molar mass of A is twice. 72 is 0.72 is twice 0.36. So the molar mass of of A is twice the molar mass of B. So I'll write that final conclusion up above. Okay, the molar mass, MM, of A, we don't know what the number is twice the molar mass of B. We just know what the relationship is. And that's all they asked us for. They asked which of the two gases contains the greatest molar mass. So we know the number's A. We don't know what the number is, we just know the number's A. Okay, that's a trick, that's a challenging problem. But we're going to get better and better at doing problems like this in the future as you learn some of the strategies. Probably a lot of you didn't know to create a ratio of the two ideal gas formulas like that, and that you could cancel these out. And you do that a lot of times, as I say, when you have a relationship but don't know an exact number. So we know we had X there, 0.1X there, so we set up a ratio of those two. Okay, let's keep going. 35 torr pressure. Okay, let's move on to number 12. So calculate the number of molecules in a deep breath of air whose volume is 2.25 liters at 37 degrees centigrade and 735 torr. Okay, so go ahead and give this a try before you get going. I'll just tell you a hint is it is going to be the ideal gas law, and see if you can at least make a dent in this. The only way you become good at these problems is try to do them. Okay, so we're going to start with PV equals nRT. And so we need to get to moles before we can get to molecules. So we've already solved this, so I'm just going to write the transposed equation. N equals PV over RT. And I'm going to plug in numbers, but before I do, I have to make some conversions. We have to convert from torr to atmosphere. Why? Because the gas constant says we have to. Gas constant is R equals, the more times you write this, the better, OH21, and it's latum over molk. So we have to have our pressure in atmospheres, not torrs. We have to have our temperature in Kelvin, not centigrade. So let's take care of this. Temperature is 273 plus 36. That's going to equal 309 Kelvin. Now for the pressure. We start with 735 torr. And go to your conversions, and we need to get it to atmosphere. There's 1 atmosphere for every 760 torr. We need torr to cancel, so cancels and cancels. So it's 735 divided by 760. And that gives us 0.97. So now everything, 0.97 atmospheres. So everything is in units that we can plug into this equation. So let's go ahead and do that. So pressure is, I'm not even going to write down my units because we know they're going to work out since we have them all correct and we know what the gas constant is. So it's PV. Volume was given to us at 2.25 liters over R, which is 0.0821 times temperature, and our temperature's up here, 309. So that's going to give us the number of moles, and that's going to be 0.97 times 2.25 divided by 0.0821 divided by 309. That gives us 0.086 moles. 0.086 moles. And it's of air. They're not specifying oxygen or nitrogen, it's just air. So that's the moles. Now they want to know how many molecules. So we say 0.086 moles of air times 6.022 times 10 to the 23rd molecule of air. Molecule's too long a word to write, so I'm just going to write air over 1 mole of air. So we simply multiply our number of moles. Moles of air cancels, and we end up with molecules of air. So let's go ahead and do that. And it's going to be 0.086 times 6.022 gives us 0.517, 0.5, just call it 52 times 10 to the 23rd molecules of air. I'm a little short on space, so if I adjust my decimal over, it's 5.2. So you made the coefficient bigger, so you make the exponent smaller. Times 10 to the 22nd, and it's molecules of air. I don't have space to write it. There it is. You can always do these problems on line paper if you want, okay, if I don't give you enough space. All right, so there's your answer, 5.2 times 10 to the 22nd power. Okay, number 13. Now, there's no way I left you enough room to do this problem, so you can do this on line paper, or you can do it on the back of the assignment, wherever you want. I don't think this is enough room. So let's read this. A container contains 1.27 moles of oxygen, O2, that should be subscript 2, 3.41 moles of H2, and 2.98 moles of N2, and has a pressure of 258 kilopascals. What is the pressure of each of the individual gases? So this goes to the principle that the pressure is proportional to number of moles. And when you think about it, that's really logical. Number of moles is how many molecules, atoms you have flying around. If you have twice as many, you're going to have twice the pressure, because you're going to have twice as many hitting the side of the container. If you have 4 times as many moles, you're going to have 4 times as many of these molecules hitting the side of the container, and that's going to be 4 times the pressure. So this is a mole fraction problem. You did this before when we did solutions, and so now you're going to do it here. So let's figure out the pressure first. Let's figure out the mole fraction first of oxygen. So for O2, this is problem 13 in your assignment. For O2, we have 1.27 moles over the total of all of the moles combined. So that's going to be 1.27 plus 3.41. In other words, it's the total moles of all of the gases combined, plus 2.98. So this is going to be the fraction of all of the gas, number of moles of gas, that oxygen has. This is the O2, this is the N2, this is the H2, and this again is the O2 here. So if I take the fraction, the mole fraction of oxygen to the total gas, and multiply it by the total pressure of the gas, which is 258 kilopascals, that's going to give me the portion of the pressure contributed by oxygen. So what I'm going to do is divide this by all 3 of these added together. So let's go ahead and do that. Let's just go ahead and do that part first. And what I get for O2 is 0.17. So basically 17% of the moles of gas is going to be oxygen. Now you multiply that by the total pressure, and that'll tell you the fraction of the total pressure that is contributed by oxygen. So multiply that 258. And that gives us 42.8, or somewhere thereabouts, take for the rounding. 42.8 kilopascals from the oxygen. And I'm off screen, so let me say what I did again. I divided this by all of these added together. I got 0.17. I multiplied that by the total pressure, so this is the mole fraction of oxygen. If I multiply that by the total pressure, you get the fraction, or you get the number of pascals of pressure that come from oxygen. It's the same ratio. Okay, so here we go. Let's do H2. And I'm just going to do this quietly, and you can do it yourself. Okay, and that's the answer to that. What are the pressures of the individual gases? So that's what they wanted to know. So there they are. Okay, let's move on to problem 14. Fairly similar type of problem. So it says a mixture containing 0.477 moles of HE. So now they're giving you the individual moles of gas, 0.28 moles of Ne and 0.11 moles of argon is confined in a 7-liter vessel at 25 degrees C. Calculate the partial pressure of each gas. So they just add one additional layer of complication. Instead of giving you the total pressure, they're going to make you figure it out right there. Okay, so let's go ahead and do that. Okay, and so the first thing we got to do is take 25 degrees and convert it to Kelvin. So do that over here, 273 plus 25. 25 degrees centigrade is a pretty common number because it's pretty much room temperature. So you're going to see this number 298 a lot. All right, so now for helium, maybe we have enough room to do this here. We have PV. Let's first solve for the equation. We want pressure. So let's just do the general equation. It's PV equals nRT. If you solve for P, you end up with P equals N RT over V. So let's go ahead and just plug in the numbers that we have. We have P for helium is going to be 0.477 moles. R is 0.0821 gas constant, and T is the number we calculated, 298. And that's going to be over the volume, which is 7. And so for helium, that's going to give us 1.67. Okay, and we're dealing with atmospheres. So that's since it's the R is the gas constant is united in atmospheres, it's going to be ATM. All right, so I don't really have enough room to do this on the same piece of paper, so let's go ahead and do neon and argon on our piece of paper down here. So for neon, we are given this 3.4, whoops, wrong one. This, which is 0.28 moles of neon. So same equation, P. Always write the equation first. It helps you to avoid mistakes. So that's going to equal 0.28. And I know my pressure is going to end up in atmospheres because I've got everything else. That's why I'm being a little careless about putting the units down, because I know what they're going to come out to be if I did all my units right to set it up. And it's again 298 Kelvin, and the volume is still 7. So the pressure for neon is going to equal and that's going to give us 0.98 atmospheres. All right, and finally we've got for argon, 0.11 moles. Let me get on screen here. Okay, if I wasn't on screen, I wasn't paying attention. N was 0.28 for neon. R is what it is. The temperature is going to stay the same at 298. The volume is what it is. It's 7. And you just run that and you get this for neon. Okay, so if you were listening to me, not seeing me, now you're seeing me. Okay, there we go. So number of moles is the 0.11 for argon. There's R, T is 298, and V is 7. So the pressure for argon and that's 0.38. Okay, so we got the pressures for each of those different components of the gas. So calculate the total pressure. You simply add them together. And this is called Dalton's law of partial pressures. So let me get this down here. So P total equals, in this case, P of helium plus P of neon plus P of argon. It's just a straight up addition relationship. Okay, so you have for helium, you had 1.67, plus for neon, you had 0.98, and plus for argon, you had 0.38. And if you add those together, you get the total pressure in the container equals 3.03 atmospheres. And that's the answer to part B. All right, few more to go. Okay, number 15, and this is simple enough, we can do it on the paper. So for each of the following balanced chemical reactions, describe what happens to the pressure after the reaction takes place. Assume that all reactants and products are gases. They're not all gases, you can't apply this, but if they're all gases, you can. So it's very simple. You count how many moles do you have on the reactant side. And here we have 2 for hydrogen and we have 1 for oxygen. So we have 3 total moles on the reactant side. Over here on the product side, we get 2 moles of water, so that's 2. So the number of moles decreases, which means the pressure decreases correspondingly. So since 2 is 2/3 of 3, you have 2/3 as many moles on this side as on this side, then you're going to have 2/3 as much pressure on this side as this side. So the pressure of the products is 2/3 the pressure of the reactants. That would be hydrogen and oxygen together. Okay, that's all there is. It's just the ratio of the number of moles is the ratio of the pressure on each side. Okay, here we have a balanced chemical equation for methane. So it's 1, 2, 1, 2. So on this side we have 3 moles, 1 plus 2 is 3. And on this side we have 3 moles, 1 plus 2 is 3. So the number of moles on each side doesn't change, so the pressure is not going to change. So the pressure remains unchanged. It's the same. Okay, finally for C, we have 1 mole of nitrogen and 3 moles of hydrogen. That's a total of 4 moles. And that produces 2 moles of ammonia. So you have twice as many moles on this side as this side. It's a 2-to-1 ratio. So you have twice as much pressure on this side. So the pressure of the products is half the pressure of the reactants. Okay, and that takes care of that assignment, and so this is due on Friday. Be sure you know how to do these. These are fundamental to gas laws, and practice those complicated problems, 11 in particular. Be sure you understand the strategy for solving that problem. Okay, we'll see you in class.